Hello everybody, this is the notes for chapter 11 that we're moving to, talking about sequence and series. We're going to do, for the most part, the whole chapter. I think we're going to skip a couple of things. But this first section, there's a whole ton of information in it. So it is on sequences and series. We're just going to start today with the sequence part of it. So what I want you to do is hit pause, try to answer these 4 questions here. What are the next 3 terms in each pattern? Go for it. All right, so things we're looking for. Just you're looking for a pattern. So to go from -12 to a -7, you added 5. To go from -7 to -2, you added 5. To go from -2 to 3, you added 5. Okay, just start with the simple stuff. Are you adding the same thing or subtracting the same thing from each term? This seems to be the pattern. Add 5. So to go from 3 to the next term, we should add 5. So there's 8. Add 5 again. Add 5. There's your next 3 terms. For the next one, we are adding 1. To go from 11 to 13, adding 2. 13 to 16, you're adding 3. Starting to see a pattern, add 4. So if this pattern continues, we should be adding 5 to put us at 25. Add 6, 31, add 7, 38. All right, to go to the third one here, to go from 2 to 6, we are adding 4, adding 12, adding, this is not looking good. So when you start to run into an issue, try something else. How else can I go from 2 to 6? Try multiplication. Multiply by 3. To go from 6 to 18, hey, look at that. Multiply by 3. 18 times 3, it puts you at the 54. So we're multiplying by 3. So 162 times 3. Yikes. Let me get the calculator out. 180, well, let's see. 300 plus another 180, 486, I think. 162 times 3, 486 times 3 again, 1458 times 3 again, 4,374. Okay, there's that pattern. For the next one, you could add 3, add 5, add 7, add 9. There is definitely a pattern there. The next number should be plus 11, 36. Add 13, you would get 49. There's a different pattern for this. Okay, so we got one pattern, but this one works a couple different ways. 1, 4, 9, 16, 25. These numbers should look familiar. What you have is 1 squared, 2 squared, 3 squared, 4 squared, 5 squared. 36 is 6 squared. 7 squared is 49. 8 squared, 64. Okay, plus 13, plus 15 still works. Different numbers, or different pattern, but same numbers of the sequence. All right, so you have an idea of what a sequence is. It is an ordered list of numbers called terms. I usually start with the first term. That seems kind of obvious, but it's going to make more sense in a minute. 2 generic types of sequences. Infinite means it continues without end. So what you'll see is those dots. It means the sequence just keeps on following that same pattern. A finite sequence, it just ends. There is a last term. All right, to get a sequence, we have there's 2 types of formulas. First one is called an explicit formula. Basically what that means is you can just find the 10th term without knowing anything else other than the formula. You could find the 100th term, the 10,042nd term, it doesn't matter. You can just jump to that term number to find the term value. And so this is where we usually start with the first term comes into play. Okay. For this example, it wants us to write the first 5 terms of a sequence. So we're going to start with t sub 1, first term. So you just plug in the term number that you want. 4 times 1 plus 5, we get 9. So the first term of the sequence is 9. For the second term, we're going to do t sub 2. So these little subscripts right here, this t sub n, those are integers, they're term numbers. So starting at 1, 2, 3, 4, fifth term, sixth term, they're integers starting at 1. 4 times 2 plus 5. So 8 plus 5 is 13. T sub 3, 4 times 3 plus 5, that's 12, plus 5, 17. T sub 4, 4 times 4 plus 5, so we're looking at 21. And t sub 5 to end this one, because we want the first 5 terms, 4 times 5 plus 5. So that's 20 plus 5 is a 25. So the first 5 terms of our sequence listed as a sequence. 9, 13, 17, 21, and 25. There's the first 5 terms of this sequence. All right, that's the idea of how an explicit formula works. It is just like a function where you're plugging in the term number to get that value. Okay, that's what it looks like. The other type of formula we have is called a recursive formula. Now this one works a little bit different. What you're going to do is use the previous terms to get to that next term. So, as an example, it says find the first 5 terms of the sequence defined by this. So, what it says right here, this t sub 1, that just means that is your first term. So we know what our sequence starts with. It starts with a negative 2. Now, what we're looking at here, in this recursive formula, we're going to find the next term, t sub n. But notice how this subscript right here is n minus 1. Remember, those subscripts are integers. So if we're looking for the second term, n minus 1 is the term before it. If we're looking for the nth term, n minus 1 is the term before that. So to find t sub 2, we're going to do 2 times the term before it, which is t sub 1, and then subtract 1. 2 times t sub 1 is negative 2, and then subtract 1. 2 times negative 2 is a negative 4, subtract 1, we're at a negative 5. All right, to find the third term, we're going to take 2 and multiply it by the second term, and then subtract 1. So to find that next term, we're using the previous terms. That's the whole idea of a recursive formula. So we're going to double the second term, which was negative 5, and then subtract 1. So now we're at negative 10 minus 1, negative 11. That's our third term. For the fourth term, we take 2 times the third term, and then subtract 1. So 2 times a negative 11 minus 1, negative 22 minus 1 is a negative 23. Okay, this is the idea of how these recursive formulas work. So we wanted the first 5 terms, so the fifth term is 2 times the fourth term minus 1. So we got 2 times a negative 23 minus 1. Negative 46 minus 1 is a negative 47. There's our first 5 terms. But that's the idea of a recursive formula. You're using the previous term or terms to get to the next term. A very famous example of this is called the Fibonacci sequence. Idea of the Fibonacci sequence is you take the, let me change the color here. You take the 2 previous terms, add them up to get the next term. 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. Okay, you're taking the 2 previous terms, adding them up to get to the next term. So we have talked about a recursive formula and an explicit formula. For the Fibonacci sequence, and you can have both formulas for a sequence. Some formulas are pretty nasty as an explicit formula, but really simple as a recursive. Some formulas are really nasty as a recursive formula, but nice and clean as an explicit formula. I'm not going to go into where this comes from. Here's your Fibonacci sequence with an explicit formula. It's nasty looking. I mean, take 1 plus the square root of 5 raised to the power of n minus, it's gross. The recursive formula. To write a recursive formula, you need to know the first term or terms, 1, the second term is 1. To get to the next term, you take the term before that one, add it to the term, 2 terms before the one you're looking for. So that would be n minus 2. There's your recursive formula. If we're looking for the third term, t sub 3, we add the second term to the first term. Okay? Very clean, very simple as a recursive formula, nasty and ugly as an explicit formula. But this is the idea of sequences. Now, we'll talk about some different types of sequences in the upcoming sections, but this is it for now.